All right, let's take a look at index of refraction, how it works, and kind of what its meaning is. So let's say we have a slab of glass here, and the index of refraction is 1.42. And we have a ray of light that's incident upon this side of the surface. And the wavelength of that light is 685 nanometers. Now some of the light will bounce right off, and that's called reflected. Some of it will go through and bend its path, and that's the refracted. And then some of it will come all the way out the other side, which is the emergent angle. Let's take a look and get started. Well, the incident angle here, let's say, is 40 degrees. Well, then the angle reflected on this side here, which is right there, is also going to be 40 degrees. So the angle of incidence equals the angle of reflection. Now, how do we calculate this angle inside the angle of refraction? Well, we measure everything for the normal, and that's what we're doing here. So we have this 40 degrees here and this 40 degrees here. So we're going to use Snell's law. N1 sine of theta incident is going to equal N2 sine of theta refracted. Okay, well, we're coming from air, so we're going to have a 1.00 initially. And we're going to say the sine of 40 equals N2, which is 1.42, times the sine of theta refracted. Okay, and after solving that, we get theta refracted equal to 26.9 degrees. And again, that's measured relative to the normal. Now, what about this ray that's emerging on the other side? Well, since we have a little bent here and it's reaching the other side, and this side's air again, and this, of course, is the glass interface here. So now we're going to find the theta emergent, okay? And the theta that we're looking at incident is going to be this angle right here. So again, we've redrawn a new normal here. So I'll just do a little mark here. That's our theta incident there. So we're going to see that we're going to reverse this. So we're going to have 1.42 times the sine of 26.9 equals 1.00 sine of theta emerging. And we're going to find out that it's 40 degrees. So what can we learn here? The angle of incident equals the angle reflected. The angle of refraction inside relative to this normal, and that angle is going to be right here, is found by Snell's law. And then when it emerges from the other side, it's going to come out at the same angle that it came in. And this is our emerging angle here, the 40 degrees. So this angle is equal to this angle. And this angle also equals this angle here. Now this works when you have something that's very symmetrical. This is a flat piece of glass. It's not like a prism, so that the light can all come out again once it enters in there. Now what exactly does the index of refraction mean? Well, we can look at it from two ways. Light comes in at the speed of light, and we'll assume that it's coming in from air, and air is very close to the speed of light. And then inside, the light slows down. So index of refraction is a ratio of the speed of light, c, divided by the speed inside the medium. That's what we're going to call it. So let's find the speed of light inside when it's inside this glass first. We have 1.42 is equal to 3 times 10 to the 8th, and we'll just divide that by letter v. And v represents the speed while it's inside the medium here. Okay, and solving that, I'll place it right here. It is 2.11 times 10 to the 8th meters per second. So light slows down when it reaches a different medium and it bends its path. What else is index of refraction equal to? Well, index of refraction is equal to the wavelength in a vacuum for the light divided by the wavelength inside the medium. And we use a Greek letter lambda to represent that. So let's find out what happens here. So we have 1.42 is equal to 685. That's the wavelength in a vacuum divided by a lambda in the medium. I'll just use letter m there. And we find out that lambda is equal to 482 nanometers. So the wavelength is shorter. So let's look at our fundamental wave equation and get an understanding here. The speed of a wave, I'll just use letter V for that, is a product, okay, of frequency times the wavelength. Okay, and frequency is given the Greek letter nu, and then times by wavelength. So look what happens in our fundamental wave equation. When light is incident upon a surface and goes inside the surface, we notice that the speed of the wave goes down, so it decreases. Okay, but wavelength goes down proportionally. And then we find that frequency is constant. So frequency is not changed when light goes into a medium, but the wavelength is, and also the speed. So we go back to what defines the energy of a wave. Well, the energy of a wave is directly proportional to its frequency. So we notice again that the frequency doesn't change. Why? Because the energy of the wave does not change. Just the speed and wavelength do. And that's how index of refraction works inside of a flat piece of glass.